So section 4.4, we're going to explore a lot of the properties of logarithms. Now we're going to start with what's called the change of base formula. In fact, I think that's going to be for calculating log base 3 of 14. So, you know, unfortunately your calculator only has 2 bases on it typically, at least on the front of the calculator. So if I want to calculate log base 3 of 14, what power of 3 gives me 14? Well, it's bigger than 2, because 2 squared is 9, or 3 squared is 9, and it's smaller than 3. That's about all I can tell you. But there's a change of base formula in case you don't have this, the ability to calculate this directly. Now, I'm going to give you kind of the simplified version of this, the practical version. You're going to take the log of x divided by the log of the base, like that. Now, technically, if you wanted to be, you know, really fancy, you could do any base. So it's really log base b of x over log base b of a, where b is some number that you can work with. But for practical purposes, I would use log base 10 for both the numerator and denominator, for which I don't need to write the 10 here and here. It's just understood. Now, how would that work out for a problem like this one? Log base 3 of 14. Well, let's take a look here. So let me switch back on my screens. Log base 3 of 14, that'd be log of 14 divided by log of 3. So let's see what that is. Actually, I'll go to decimals for that first one. Shut these off and just type it in down here. Log of 14, close parenthesis, divided by log of 3. And it makes sense. I expected something between 2 and 3, and we got it. So 2.402. Now, in my last video, I showed you how to find log of any base. But what I'd rather show you is how to find that on your calculator. So the cool thing is that you can do this directly on your calculator. So if you go to the math button, and I think we might have to go to number. Is it number? No, maybe wrong. Here we go. It's near the bottom of the math menu. So that would be log base. That's what you want. If you type the math key and then alpha and A, it'll jump you right down there. Log base 3 of 14, bam, 2.402, et cetera, et cetera, et cetera. Now let me write that together a little bit more here on my sheet. Log base 3 of 14 equals 2.402. Can anyone write that as a statement using exponents? What would be the equivalent statement? And by this bidirectional arrow, I mean is equivalent to. How would you write that using exponents? What to what power equals what?
3 to the power of 2.402 equals 14.
Perfect. 3 to the power of 2.402 equals 14. Now, this could be an extra credit question on an exam sometime. You know, prove that you got it right. Well, what you could do is rewrite it, and you want to do 3 to this power. And you know what? I don't feel like typing in that power. So what I'll do is I'll raise it to the power of answer. Where is answer? If you hit the second key, then the opposite key, right next to the enter key, second and then answer, that should give me 14. Exactly. And it does. It nailed it. So once again, let me clear this out here. Let me go back up here. Type that one in. And I'll do 3 raised to the power of answer. And you can see the keys that I'm pressing on the bottom row here, my key history. There you go. 3 to the power answer equals 14. So nice. A nice little thing to keep around. Now I can't do this again because this answer variable now has the value of 14 in it. So if I did 3 to the 14th, I get a really, really big number, but at least it helped me check it for that one. Okay. Do you want to practice that one again? Use a change of base formula to calculate log base 7 of 10? Yeah, why not? Why don't we calculate one more here just to make sure we're good with that. So I'll clear this out. Math. And then I'm going to just do alpha A. That's a quick jump down to what I want, log base 7 of 10. Now I can't use the log key because that's for log base 10. All right, I've got log base 7. So it should be a number between 1 and 2 because 7 to the first power is 7. 7 to the second power is 49. So yeah, 1.18. How do you prove you got it right? Well, you could do 7 to this power should equal 10. So to practice that, let's clear this out. 7 raised to the power of my previous answer. Second button and then the opposite key. Bam. 10. Nailed it. All right. Is that answer key a new trick for you guys on your calculator? All right. It's a good one. Let's keep going. Now, there's a lot of formulas and a lot of problems that we're going to work with in the next couple sections, and they're all going to relate to and rely on the fact that we have some rules for logarithms. So let me give you all the rules for logarithms. You know, I'm going to put it on a separate clean sheet here because I'm going to come back to that and refer to it. So, rules for logarithms. So the first three I'm actually going to give names to, and they actually come from your rules for exponents. Remember, properties of exponents or logarithms are the inverse of exponents. So for instance, a to the n times a to the m. When you multiply things with the same base, what happens with their exponents?
Well, you add them.
You add them. And likewise with logarithms, so log of a times b is going to be the log of a plus the log of b. Okay. That's our product rule. Now, I'm not going to quiz you and say what's the product rule, but you know, eventually you've got to know it. But I'm not going to ask you for it by name. Let's go back to logarithms here, or exponents here. A to the n divided by a to the m. When you divide things with the same base, please don't cancel out the a's. When you divide things with the same base, what happens with their exponents?
Subtract.
You subtract. Cool. And when you divide in the logarithm, you're taking the log of a divided by b, that's going to be the log of a minus the log of b. And that's our quotient rule. And we got one more that I'll give a name to. I'm not going to try and derive this one like I did the other ones. If you have log of a to some power, then that r can kind of jump out in front like this. I sometimes call it the parachute rule because it feels like r is jumping out, parachuting out front. But that's your power rule. And that's great. Now, there's 4 more properties of logs that I would suggest you know. 2 of them are crucial. 2 more are just handy. So let's take a look at those. The first one maybe we can figure out log base b of 1. Now in all of these, I haven't written a base. You know, I could write whatever base I want here. Base b, base b, base b. I haven't taken time. It's not as if this just applies to log base 10. It doesn't. But it becomes kind of tedious just to put in all these bases. So just know that it applies to all the bases. And as a reminder, b is greater than 0 and different than 1. But let's see if we can't think our way through this one. What power of b gives me 1? B to the what? Would give you a 1. What's exponent? Yeah, there you go. B to the 0 power equals 1. Let's look at a similar one. Log base b of b. What power of b is going to give me b? That would be to the first power. So when the base and the number match, then it's just a 1. When you take the log of 1, you get 0. Let's take a look at a couple more here. What if I had log base b of b to the x? Now, I'll show you how you can kind of prove this one with ones we've already got. Let me see here. Yeah, this would be good. I'm just going to write the result eventually, but one of the things we could do is we use our parachute rule. That x can come out in front. So this would equal the log base b of b times that x, which is now out in front. But what did we say just a minute ago about the value of log base b of b? What is that equal to? That's just a 1. So the bottom line is that you get x times 1, which is just x. Or in other words, here, log base b of b to the x is x. And the last property that we're going to want, kind of similar to this one, is b to the log base b of x is also x. And what's going on here is something that we saw a while ago when we were talking about inverse functions. When you do a function and then its inverse, you get back to x. Function and then its inverse gets you back to x. That's exactly what's going on here. So if I did the cube root of x cubed, I'm going to get back to where I started. I'm going to get back to x. You're getting exactly the same thing here. Now there was a few things in the last section that I don't think I went through. So let me see if we can't take a look at some of these things now. Some values from, let's see, is it this one? Yeah, right here. Some of these. So we'll do example E to start with. And these are properties that I just mentioned here in 6 and 7. So what I want you to notice here, and I guess as I write things here, I'm not sure what it calls. So 5 to the log base 5 of 6. What you should notice is that the base of the exponent and the base of the logarithm match. So 5 to the log base 5 of 6, that's actually going to be kind of challenging to put into your calculator or even the Desmos, but the answer is not challenging. The answer is just 6. Let's try another one like that. 4 to the log base 4 of 26. And then the last one is e to the ln of 20. So, Let's see if we can't simplify that. How about the middle one here? That one's a little bit easier than the other two, or than the next one. What's 4 to the log base 4 of 26? So the thing that I want you to notice is that those two things match. And when those two things match, as they do, say, right here, then they cancel out. And what you'll end up with is just the exponent. Or in our case, 26. Now it's a little less clear what's going on here because they don't match, right? Or do they? Keep in mind that ln is really just fancy notation for log of what base? What base is understood to go along with the logarithm? Like the natural log? E. So once again, the bases match. The base of your exponent and the base of the logarithm match. So that means these things cancel each other out and you get 20. You could actually do that one on your calculator without too much fuss. So let's clear this out, clear that out. Second e to the ln, so you got to hit this again, of 20 should equal exactly 20. Perfect. That's exactly what happens. All right. How about a couple more here? E to the ln of 1 over pi. And then, well, I guess I skipped over one, e to the ln of the square root of 7. And finally, 10 to the log of 15. So let's take a look at all those. All right, Spencer, maybe you can do that one. Sia, you've been helping out. So Sam, maybe you can do the first one, and Katie, the middle one, please. So, whenever you're ready.
The first one?
Yeah.
That would be 1 over pi.
Yeah, 1 over pi. Yay! And Pi Day is coming up pretty soon, right? March 14th. Yay. Katie, second one.
I forgot where the pi button was.
Pardon?
I forgot where the pi button was on the calculator.
Oh, the pi button is above the exponent, the exponentiation key. But you don't really need to resort to calculating this on the calculator. I'm hoping that what you'll see is that even though it's not written that way, the bases involved are kind of the same. This is e to the log base e of the square root of 7.
Okay, sorry, I was looking at the wrong one. I was
Okay, I might have mixed
Okay.
up a little bit.
Um,
So what would this equal? Does that simplify at all?
um,
So let me help out. These are equal. And when those are equal,
this equals the square root of 7.
yeah, just going to get the square root of 7. They cancel out and give you the exponent. Awesome, thank you. So got that one and that one. Spencer, even though it's not written, what base is understood to go along with that logarithm? And yeah, that would be a 10. Log base.
15.
Yep, perfect. 15. Thank you so much. Yay. So it's a very handy property, and that one gets used a lot. Both of these get used a lot. That the logarithm is the inverse of the exponential, and the exponential is the inverse of the logarithm. So very, very handy. That's why I wanted to write it on a separate sheet there. Let's go back to this one. Let's combine some of these expressions to write it with one logarithmic term, and then we'll go the other way as well and expand our logarithms. Let's see, do I want to start with expanding logarithms, or do I want to? All right. There's a couple ways you can do these, and we'll get around to example B in a little bit. But let's start out with example C. It says use the laws of logarithms to evaluate the expression. And so I realize that there's a lot of ways you can do this that don't rely on the laws of logarithms, that just rely on your calculator. That's fine. But let's see if we can't stick to the spirit of this. So example C. -1/2 log base 5 of 25. So I believe the authors of this problem really want you to notice this. You got a 5 here and a 25 here. It might be a good idea to write that as, not as 25, but as 5 to the second power. Okay, that's kind of cool. But now we can use our properties here. In fact, there's a nice property that we can use that just about solves this right now. Can anyone tell me what this expression is going to be worth in the parentheses? It's just going to be 2. Because once again, the base and this base match. So you're just going to get the exponent, which is 2. -1/2 times 2 is going to be -1. Yay! So in mathematics, sometimes, if you're reading some higher math, the proof of things can go on and on for pages. And to let the reader know that, okay, we're finally done, they put this little Latin abbreviation, quod erat demonstrandum, that which was to be shown. But to make it easier in this class, we can remember this as quite elegantly demonstrated. Don't forget to tip your servers. I'll be here till 10. All right, let's try some more here. Log base 2 of 2 to the 1/2. So again, sticking with example C here, log base 2 of, I actually read it as 2 to the 1/2, but I shouldn't have done that. I was kind of doing your work for you. That's the square root of 2. But since I already let the cat out of the bag, that's log base 2 of 2 to the 1/2 power. Because remember, square root of 2 is also 2 to the 1/2 power. And you're going to have to do that a lot with logarithms. It's convert things back and forth between exponents and radicals. That's because there's no specific property that deals with radicals. It's all done with exponents. So if you're stuck with a radical, change it to exponential notation. But this is another example just like this. These bases match. What's our answer here? 1/2. Excellent. Thank you. Okay, another one. Let's keep rolling. This was actually kind of an interesting one. There was a problem earlier that I'm like, ooh, I haven't seen one like that before. And it was interesting because it was novel. Usually I can just look at these things and just know. But this one, a little bit creative. ln of the ln of e to the 100. So, wow. Let me think about how I want to approach this one. Well, whenever you've got a nested set of calculations, you always work from the innermost parenthesis out. And in this case, I've got the ln of e to some power. So, is it worth it? Should we? It probably wouldn't hurt to recall that this is log base e here. So it's really log base e of log base e of e to the e to the 100. So all I'm doing is I'm replacing the ln notation with log base e. And this whole thing here in the parentheses, the pink parentheses, is an exponent. So I'm going to take and bring that out in front like this. So it's going to be log base e, log base e of e. So what happens is that this exponent comes out in front. And I know it's an ugly, uncomfortable exponent because it's an exponent itself, e to the 100. But this whole thing comes out in front. And now I've got something I can dig my teeth into a little bit. I'm going to worry just about this part. Log base e of e. And I want to simplify that. And I'll give you a clue. One of your 7 properties here helps us out. Which one of our properties is going to help us out with log base e of e? Any takers? Well, the thing to notice about this is that the base and this is the so-called argument because you're taking the log of this. These two things match. And that's the same in property number 5. Log base b of b is 1. What power of b gives you b? B to the first power. So this is a 1. So that's the big thing on that one. The rest of this I'm hoping is going to go a little bit easier. I'll pause. Are you okay with our first couple steps here? Because I know, especially this first one, might be a little bit uncomfortable. That's an exponent. Came out in front. We used our power rule for that one. So that's out front. I'm going to ignore that. Log base e of e is 1. So it leaves me with log base e of e to the 100. And now I can use another property of logs to finish this one up. So what would that equal? Or what property should I use? Back on my other sheet. Does anyone see a property that applies here?
Number 6?
Yeah, well done, number 6. The bases match and I got some exponent. So what you end up with is 100. Beautiful. Thank you. Now, let's try a couple that are just really practicing some different aspects of our rules of logarithms. We're going to expand these into the product and sum of different logarithmic expressions. So the first one, we've got log base 7 of 5x squared over y cubed. All right. So I want to use the quotient rule, the product rule, and the power rule until we're all exhausted with that. That is, you can't apply that anymore. So to start off with, the first thing I see, I mean, I see some exponents and products and stuff like that, but the product is only in the numerator and the exponents only apply to individual terms. So the first thing you really see is that this is a quotient. And because of that, we're going to use the quotient rule. So that's going to become the log of the numerator, which is 5x squared, minus the log of the denominator, which is y cubed. So that's the first thing. But please don't stop here, because there's a lot more we can do in terms of using our power rule and our quotient rule. Oh, that's log base 7. I should include the 7 here and here. Now what else? Well, for the second term here, the 3 can come out in front, so it'll be a minus 3 log base 7 of y. So, okay. But I can't bring the 2 out in front because the 2 only applies to the x. I can regard this as a product though. So let me do this so you can kind of keep track of where this goes. That is going to get expanded into the log base 7 of 5 plus the log base 7 of x squared. I'm almost done. Can anyone see one more thing I can do before I'm exhausted with my product rule, quotient rule, and power rule?
Put the exponent in front.
Yeah. The 2 comes out in front. And that'll be it for this one. So I end up with log base 7 of 5 plus 2 times the log base 7 of x minus 3 times the log base 7 of y. Beautiful. All right. Let's try another one. The one below that. So log of y to the 9th over the square root of 5x. Now, in a sense, this is kind of like the last one. It's like the last one because the first thing you see that we can really dig our teeth into is that we've got a quotient. You can't bring the 9 out here because the 9 only applies to the y. If I had the 9 outside the parentheses, if that 9 applied to this whole expression, then I could bring it out. But that's not what I've got. So I'll write this as the log of y to the 9th minus the log of the square root of 5x. Well, the 9 can come out in front. Log of y minus, and I can't really bring anything out in front just yet because I got to rewrite that. I got to write that as the log of 5x all to the 1/2. Make sure that it's parentheses, and into the parentheses is a 5x, and all raised to the 1/2. And now I can take the 1/2 out in front like that. So that's going to be 9 times the log of y minus 1/2 times the log of 5x.
I have a question.
Yes.
Where you expanded it out to where log parentheses y to the 9th, since it's still in the parentheses, why did you move it out to the front?
Oh, I wanted to get it out of, I wanted to use the power rule. So the idea is to try and expand this as much as
Right.
possible using your power rule, quotient rule, and product rule. So
I
all
guess
three of
because I
these big
just
ones.
Oh, sorry. I understand that. I guess because I just saw that it was still within the parentheses,
Oh,
that you can't move it to the front yet.
yeah, the parentheses is just, the reason I put that there is just to kind of say, all right, we're taking the log of this. So what you take the log of is called the argument. So I didn't really need to put the parentheses there.
Oh, it's
I'm
just
sorry,
trying to like
was-
separate it?
it was just, it's just for you visually. Like I could have put parentheses
Okay.
around this. And that's just a visual thing, just to say, all right, this is what we're taking the log of. So your older versions of your TI-84 graphing calculator would do kind of the same thing. Now when I do the log here, it says, all right, well, what are you taking the log of? And you need parentheses around that. So
Right, okay.
it's just kind of a habit for me to sometimes use parentheses. I apologize that I'm not 100% consistent in doing
Oh,
that.
no, I just wanted to make sure that, there wasn't an actual parentheses there, because I saw that from the previous, problem. It
Yeah.
was log 5x
Right.
squared, yeah,
Yeah. So again, the
Okay.
parentheses there is just for our visual convenience. And we did have a product here, and we split it up, said, okay, that's a log of 5 plus a
Oh,
log
okay,
of
I
x
see, I
squared.
see.
All right?
Okay.
And all
I
that
see
was
the
just in
separation.
here. Okay?
Oh,
No, but it's a
understand.
great question. I'm sure you're helping somebody out here, and I appreciate you chiming up.
Thank you for clarifying that.
Yeah, no problems. Now, let's see if what I said helps you out to catch my mistake. Because I'm going to make a mistake as I write down this next line. It's going to be 9 log y minus 1/2, and I'm going to use the product rule here. So it's going to be 1/2 log of 5 plus log of x. So I used the product rule to expand that part there. But there's a mistake. What's the mistake? It's subtle. And, especially late at night on a long day, I don't blame you if you miss that. But let's put this in parentheses. And that means I'll put that in parentheses here. So that if I was to write this without parentheses, then that 1/2 has to distribute itself to both terms. Log y minus 1/2 log of 5. But initially, without the parentheses, I just had plus log of x. It should be minus 1/2 log of x. In other words, that 1/2, that minus 1/2 has to distribute itself to both terms. So you can either write it with parentheses, and that's fine, or without parentheses, and that's fine. You just got to distribute that negative 1/2 to both terms. So you got to be careful when you expand something and it has a coefficient, that coefficient applies to all those terms that follow. So kind of a little tricky there, annoying maybe, I know, sorry. Don't shoot the messenger. All right, but that's it. That's as far as you can go. You've expanded that as much as possible. All right. Let's see here. Let's look at another problem of expanding. So we'll look at this one. Expand. And here's one possible answer, although I'm not suggesting that I'm actually going to give much credit for it. But if I ask you to expand the log, then this is possible. All right, now she gets it. All right, this is good. All right, a little bit of a joke there. Glad you got it. She's smiling with her eyes. That's good. Thank you. Let's actually look at that one though and figure out how to solve it the right way. So ln of the square root of x to the 9th plus 6 Now, my properties for logs apply to ln just like they do anything else. I'm going to start like this, write it as ln of x to the 9th plus 6. Well, what power should I put here?
1/2.
To the 1/2. And then that 1/2 can come out in front. And I'll end up with 1/2 the ln of x to the 9th plus 6. What can I do from here? Ooh, well done. Yeah, I think that is the right answer.
It's very close.
Yeah, I know it's tempting to want to say, oh, well, you can do the log of x to the 9th plus the log of 6. No, you can't. If you look back at all our rules, there's nothing that says you can take the log of a sum and turn it into the sum of the logs. There has to be a product in order for you to split it up like that. There's nothing here that allows you to split up a sum. That's it. You're done. So, QED, right there. Excellent. Excellent. Here's a couple other ones that are a little bit more challenging. So, let's see on these. I'll start with the one here. Log base 9 of x times x squared plus 3 over the square root of x squared minus 3. So give me a second to copy that down. Log base 9 x times x squared plus 3 over square root of x squared minus 3. Now, I would suggest that we not distribute the x, rather that we'll leave it here. But I am going to start out by doing one thing first, and that is I'm going to rewrite the denominator. Suggestions on how to rewrite the square root of x squared minus 3 in a way that might be useful to us here. X squared minus 3 to the 1/2 power. The reason I did that is because I know eventually I'm going to want to use the power rule for this thing. Walk me through it. What's the first rule that I should use for this one? Power, quotient, or product rule?
Quotient?
Yeah, quotient. You have to use a quotient because, you know, this x is not written as the product of the whole thing, so it's just the numerator. You've got something divided by something else. Yeah, we're going to start with the quotient rule. Log base 9 of the numerator, x times x squared plus 3, minus log base 9 of the denominator, x squared minus 3 to the 1/2. Now there's different things left in different parts of this. In the first part, well, I've got a product. I've got this times this. So that becomes the log of 9. And the log of a product becomes the sum of the log. Log base 9 of x plus log base 9 of x squared plus 3. What rule am I going to use in this last part?
Power?
Yep, power rule. So it's the log base 9 of x squared minus 3. Can I do any more work with that last term there? Log of x squared minus 3, or perhaps do some work with this one, log base 9 of x squared plus 3. Is there anything else I can do with either of these terms? That's it. There's no rule that allows you to take and split up the log of a sum. Likewise, there's no rule that allows you to split up the log of a difference. You're done. Done with that one. Oops. This one is the one I was talking about earlier that I'm like, oh, that one's kind of cool. That one's kind of challenging. So let me copy this one down. That'll be the last of the ones we practice with expanding logs. And then we're going to kind of go the other direction. We're going to contract them. So let's take a look here. It's log of the square root of x to the fifth, square root of y, square root of z to the fifth. Wow, kind of a lot going on with this one. But if we're careful, it should work out pretty good. So let's take a look here. I'm going to start out with this term here in the parentheses. And rewrite that, let's do the log of the square root of x to the fifth as the square root of y. But instead of square roots, I'm going to write this as z to some power. And we got to think carefully, well, what's that going to be? So you got square root of z to the fifth. And if it helps, maybe it helps a little bit to think of there being a 2 out in front here. Does anyone remember how to rewrite this using rational exponents? What power would that be? Oh, it's all right. I'll help out. So the 5 comes up, the 2 comes under. It's z to the 5 halves is what you're going to have there.
Oh yeah, that's right.
So z to the 5 halves. Let me kind of squeeze that in here. And now I'm going to play that same game with this term right here. I've got, maybe I'll do that over here. Y to the z, or y times z to the 5 halves. And I'm taking the square root of all of that. So that kind of puts a 1/2 out in front. Or 1/2 is an exponent. So something to 1/2 powers, that's just like a square root. Except instead of writing with roots, I'm going to write it with exponents. That 1/2 is going to multiply each of these exponents. So it would give me y to the 1/2 times z to what power?
5/4.
5/4. Well done. All right. So this is going to become log of x to the fifth times y to the 1/2 times z to the 5/4 all to the 1/2. Now I'm doing it all to the 1/2 because we're taking the square root of all this. What happened to my nice orange marker? So all of this is under the radical. Taking the square root of something is like raising it to the 1/2 power. So I've got one last little game to play with all of these. And that is take 1/2 times each of these exponents. So that's going to give me the log of x to the 5 halves plus, or excuse me, not plus, how about times y to the 1/4 and z to the 5/8. Whew. So it took a lot of work to get this in the right form, but the rest of it I'm hoping is not going to be too bad. So I'm just going to copy that over to here. Log of x to the 5 halves, y to the 1/4, z to the 5/8. This is a log of a product. And to spare you a lot of inconvenience in the future, the log of a product turns into the sum of the logs. So it's a log of x to the 5/2 plus the log of y to the 1/4 plus the log of z to the 5/8. Okay. Who wants to deliver the final blow here in this problem? Time for this problem to go away. The 5/2 comes out in front. 5/2 is the log of x plus 1/4, the log of y plus 5/8, the log of z. Yay! That's it. Now this part right here is actually kind of a crucial thing. Actually going from here to here or the other way around. The other way around we use quite a lot, and we're going to be doing that next. But what I want to point out is that if you're going this way, that the sum of the logs became the log of a product. So it's just this, this, and this, the log of the product of those. And so I want to practice that idea with this example. I want to turn the sum of the logs into the log of a product. And I'll give you a nice, easy one to work with. So here you go. And that's a log here. I just vacillated between using cursive and regular print. But see if you can't turn that into the log of one term. That is, go backwards, which is where we're heading next. All right. I don't hear any howls of laughter, but maybe it's not all that funny.
Yeah, I know I know. Oh, I'm sorry. I just noticed that.
All right. A couple of you are getting it. Log cabin. Ha 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 ha. Yay. All right. It's not too often I can sneak in a little joke like that into your math class. So give me some love on that, all right? I had to wait an entire semester for that. Okay. All right. But this is actually a good example because it's really convenient to just shove those things together and get the log of all of those things multiplied together. And that's where we're headed next. We're going to go in the opposite direction of what we've been doing. Instead of expanding the logs, we're going to kind of contract them and put them together. Now, the reason for these is these are all properties you're going to have to use in section 4.5. So that's why we want to get good at them here. And let me show you with this next example, example F. Now, the one thing I want to point out about the one we just did is that all the coefficients here were 1. I had a 1 here, a 1 here, a 1 here, a 1 here, a 1 here. That's crucial. In order to bring these together as the log of the product, all these coefficients have to be 1. So how does that impact us for a problem like the first one in number F? Well, let's see. Let's see, so we've got 3 ln of 2 plus 4 ln of x minus 1/2 ln of x plus 3. Now, I've got a unique style of solving this. It might not match some of my colleagues, but I think it's the fastest way that you can do these things. My goal is to write this with one logarithmic term. And what I'm going to do is I'm going to start by bringing these terms up into the exponent. So that would be ln of 2 cubed plus ln of x to the fourth. And where I might be different than my colleagues is I'm not only going to take the 1/2 into the exponent, but I'm going to take the negative 1/2 as well. So it's going to be plus ln of x plus 3 to the negative 1/2. So we're okay with that? I just used the product rule in an opposite direction. Or I mean, not the product rule, the power rule. So the power rule would say bring it down, or in the other direction, the power rule says, oh, you can take it up. But here's where we're going to apply our log cabin rule, right? Because all these coefficients are now 1. So 2 cubed, what is that? That's 8, right? So I'm just going to write that as the ln of 8, x to the fourth, and then x plus 3 to the minus 1/2. Wow. Now on an exam, I'll probably ask you to get rid of the negative exponent as well. Now that negative exponent only applies to this term right here. So the way you can do that would be the ln of 8x to the fourth over x plus 3 to the positive 1/2. And you're done. Sweet. Nice.
Is there a reason why you chose to, instead of leaving the minus there and just putting it to the half exponent, why you wanted to make it a +1 instead? If that makes sense.
Make it a positive exponent?
Yeah.
Yeah, it's the way these problems are asked quite a lot. But it also makes it easier to write this as something involving the square root. I mean, most of you probably wouldn't just say, oh, well, that means square root in the denominator. I think it's a little easier to see that way.
Would it be easier in more complicated problems? Would you, is that how you do it? Or?
You know, my MO on these things is always going to be to get rid of everything right off the get-go that's in front of my logs. That way the coefficient is 1, 1, and 1. It just makes it a lot easier. Look, I could show you a dozen different ways to do this, but it gets messy because you got to use the quotient rule, and the quotient rule is only going to apply to this and not to these, and you got to use the product rule here, and it gets messy, especially if I had 2 of these that are negative. Then that becomes even more of a pain. So I think this is the most efficient way. Can you do it other ways? Absolutely. Am I going to mark you wrong if you do it my something other than the way I do it? Absolutely. No, I'm kidding. There's a lot of ways to do these, and you don't have to do it my way. When I show you things in class, I try and show you what I think is the most efficient way. It may not be the fastest way, but it's going to be the best in terms of the least confusing and the least likely to give you an error. So, all right. Let's try a couple more here. We'll go with this next one. 3 and then parentheses log base 7 of x plus 3 log base 7 of y minus 5 log base 7 of z. Personally, I think I would start by distributing the 3 to all these terms inside rather than dealing with some cube term at the end, and get log base, or excuse me, 3 log base 7 of x plus 9 log base 7 of y minus 15 log base 7 of z. And if you want to pause the video for a second, give yourself a chance to try the rest of this, that's great. If not, then maybe somebody here can tell me, what step am I going to do next? Here I want to get rid of the coefficients. I want 1 in front of all of these to do things the way I like. So it's going to be log base 7 of x cubed plus log base 7 of y to the 9th plus log base 7 of z to the negative 15th. And here's that little place I wanted to be. I wanted to have coefficients of 1, 1, and 1 all the way through. That way I can rewrite this as the sum of logs. Log base 7, which means the sum of logs becomes the product, the log of the product. So log base 7 of x cubed, y to the 9th, z to the negative 15th. And like the last one, I'm going to ask you to get rid of the negative exponent. So it'll be log base 7. These two stay in the numerator. X cubed, y to the 9th, over z to the 15th. Yay. A lot of variety in the way you do these things. You don't have to show me every last step, but I want to see some of your work there. Something that lets me know that you know what you're doing. Are you kind of getting good with those, combining the logs ones? You want one more, or are we good? It's up to you. Okay. Somehow or another, think that you've got one of these types of problems that might be in this example of the homework, or this set of the homework as well. So let me just take a quick look here on Desmos and talk to you about the different shapes of the graph of a log. So one of the things you'll see with the graph of a log is that its domain is 0 to infinity. That is, it starts at 0, goes out towards infinity. It doesn't actually include 0 though. Now if I did log base 5, notice it takes log base 5 longer to grow than it does log base 2. So, okay. And E is between 2 and 5, so its graph is between 2 and 5. 10 is bigger than 5, so 10 should take even longer. And we can kind of figure that log base 10 of 10 is going to be 1. So that graph should pass through here, like that. Now, there's one feature in common of all these graphs, and that is that it passes through 1, 0. Right? Because remember, this is the opposite of our exponential graphs. And our exponential graphs, graphs like y equals 2 to the x, they're going to pass through 0, 1. Remember, they're mirror images of each other around the line y equals x. So when you look at these graphs here, it says, draw the family of functions for these different bases using the screen. Why can't these graphs be the right ones? Well, I mean, one of the things that's wrong with this one is that it's in the wrong order. The smaller the base, the faster it'll grow. So it should be in an order like this. But both of these have something that's glaringly wrong. What is it? How come neither of these could be the right set of graphs? Yes. A couple of you chiming in there. Thank you so much. Yeah, they don't pass through 0, 1 or 1, 0. All right, end of story. So, nice. Okay, that'll do it for section 4.4. Good luck on the homework.